Welcome to Introduction to Composites. Today is the last day of the ongoing week, and over the last 5 days what we have done successfully is we have developed mathematical relationships between stress and strain for especially orthotropic lamina. We have also exhibited and shown the mathematical relationships between stress and strain for a generally orthotropic lamina. And in the last class what we did accomplish was we started developing relationships between elastic constants as applicable to generally orthotropic lamina, which are Ex, Ey, Gxy, Mx, My, Muxy, Muyx, and the elastic constants for especially orthotropic lamina El, Et, Glt and Nult. And what we have shown is that specifically that Ex, Muxy and Mx can be expressed in terms of El, Et, Glt and Nult. Today we will develop the remaining relationships, and at the end of the course at the end of this day we will show that all the elastic constants for generally orthotropic lamina can be reduced in terms of simple functions for which are applicable for especially orthotropic lamina. So, today, the next phase is that we will develop relationships between Ey, My and nu xy or actually nu yx. We will develop relationships between these things to special orthotropic material properties, which are El, Et, Glt and Nult. So, we will develop these three relations. For the first set of relationships, we had loaded the material in the x direction. Now, what we do is we load the material in the y direction and we will get similar relations. Okay. So, here what we have is we have this material and this is my x direction, this is the L direction, this is my transverse direction, excuse me, and this is my y direction. And instead of loading this sample in the x direction, I applied a pure tensile load in the y direction. So, I apply sigma y here. The angle between L and x axis still is theta. So, this angle is still theta, and if we exactly follow the process which we had discussed earlier, so then we end up with the relationships between Ey, My and gamma yx and these terms. All the other steps are similar, are very much the same. So, we do not have to repeat it. So, what I will do is I will directly write down the relations. So, the first relation is for Ey, Young's modulus in y direction. So, this is 1 over Ey and that equals sin 4 theta over El plus cosine 4 theta over Et plus 1 over 4 and I have 1 over Glt minus 2 Nult divided by El sin square 2 theta. So, this is the relation for Ey, and to get to this relation we have to follow exactly the same process which we did earlier. The next relation is for My. So, My, actually before My we will express the relation for gamma yx. So, gamma yx is equal to nu TL over Et and this is 1 over E y on the right side minus 1 by 4. So, it is nu T L over E t minus 1 over 4 plus 1 over E L plus 1 over E t plus 2 nu L t divided by E L minus 1 over G L t sin square 2 theta. So, this is the second relation. And the third relation, so there is little confusion on the left side. So, I will just make it explicit. So, this is nu y x divided by E y, and then the cross coefficient m y equals sin 2 theta times this entire thing nu L t plus E L over E t minus E L over 2 G L t minus sin square 2 theta, oh actually I am sorry, sin square theta times 1 plus 2 nu L t plus E L over E t minus E L over G L t. So, these are the three relations, and so we will call them D3, D4, D5 and D6. And when you compare D3, D4, D5, D6 with their counterparts D1, D2, D3, what you find are some equivalences, and that is gamma xy equals minus mx sigma x over EL, and you also see that my equals minus gamma xy times EL over sigma y. I mean, these are the basic definitions. So, we use these definitions to develop the relations mentioned earlier. Finally, we will develop an expression for gxy. We will develop an expression for gxy. So, what do? We again go back to our basic concept. We have a orthotropic composite lamina. The lamina is loaded in this direction, is not especially orthotropic, and so this is my x axis, this is my y axis, this is my L axis, and this is my t axis. So, the angle between x and L axis is theta, and here since we are interested in finding gxy, we subject it to pure shear stress, okay, positive shear stress. So, this is our positive shear stress is applied like this. So, this is tau x y. So, in this case sigma x is equal to 0, sigma y is equal to 0, and tau x y is not equal to 0. So, the first thing we do is we express sigma tau x y, from tau x y we compute sigma L, sigma t and tau L t. So, we say from those stress transformation equations, tensor equations, sigma L is equal to 2 tau x y sin theta cosine theta, sigma t equals minus 2 tau x y sin theta cosine theta, and shear stress sigma tau L t is equal to tau xy cosine square theta minus sine square theta. So, these are the things. So, if this is the case, and then we also write, now sigma L is going to be a source of epsilon L and epsilon T. Sigma T will also generate epsilon L and epsilon T, and tau LT will generate a shear strain. So, we can, from these things we can write expressions for epsilon L. Epsilon L is what? Sigma L over EL minus nu TL over ET times sigma T, and from this we get 2 tau xy sin theta cosine theta in parenthesis 1 over EL plus gamma TL over ET. Okay. The negative sign goes away because we have a negative sign here, and tau sigma T is also negative. So, that is why it goes away. Similarly, epsilon T is equal to sigma T over ET minus nu LT times sigma L over EL, and if we do all the mathematics we get 2 tau xy sin theta cosine theta nu LT over EL plus 1 over ET, and finally gamma LT equals tau xy by GLT cosine square theta minus sine square theta. Okay. Now, we realize, but if we do the strain transformations calculations, we realize that gamma xy can be expressed in terms of epsilon T, epsilon L and epsilon LT using this relation, 2 epsilon L minus epsilon T sin theta cosine theta plus gamma LT cosine square theta minus sine square theta, and it is nothing but same as tau xy over gxy. So, if I combine, if I put, so let us call this as equation E and this is F. So, if I put E in F, what I ultimately get is 1 over gxy equals 1 over EL plus 1 over ET plus 2 nu LT by EL minus 1 over EL plus 1 over ET plus 2 nu LT divided by EL minus 1 over GLT cosine square 2 theta. So, this is the last expression, and that is for the shear modulus in xy coordinate system. So, this is from the third equation. This is for if we use the equation for gamma xy, and if we use the equation for epsilon x and epsilon y, we will see from that again we will see that epsilon x is equal to, it will get this relation, and epsilon y equals minus my tau xy divided by EL. We will get the same relation which we had written earlier. So, mathematically we have shown this. So, what we have accomplished in last several lectures is we have established concrete mathematical relationships between the 4 elastic constants which are mutually independent for a specially orthotropic plate, and we have expressed all other elastic constants Ex, Ey, Mx, My, nu xy, nu yx and gxy in terms of these 4 elastic constants. Finally, we will do an example so that we become conversant with all this, and here we will actually calculate strains for this system. Okay. So, we have this is my x axis, this is the y axis, and this is my L axis, this is my T axis, and this lamina is experiencing several stresses. So, it is experiencing a negative sigma x and the value is minus 3.5 MPa. It is experiencing a positive sigma y and this value is 7 MPa. And finally, it is experiencing shear stress. And this value is 1.4 MPa. So, given this stress state and the material properties which are EL is equal to 14 GPa, ET is equal to 3.5 GPa, GLT equals 4.2 GPa, and nu LT is equal to 0.4 and nu TL is equal to 0.1. So, these are the 4 5 material properties we already know in the LT plane. So, this is given. We have to find all the stresses and strains. So, we have to find epsilon x, epsilon y, gamma xy. So, how do we do this? So, first we identify what are the values of sigma x, sigma y and tau xy. So, sigma x is how much? Minus 3.5 based on the picture, sigma y equals 14 and tau xy equals, excuse me, it is 7, yeah, and tau xy is minus 1.4. So, it is important here the stress is, shear stress is negative. So, this is the stress state from the material properties, and theta is given to be 60 degrees. So, given this value of theta, we first calculate Ex, Ey, Exy, Gxy and so on and so forth. So, we find that Ex is equal to 5.02 GPa, Ey is equal to 10.87 GPa, Gxy equals 2.7 GPa, nu yx, oh excuse me, I will write that in separate thing, nu xy divided by Ex is equal to nu yx by Ey, and that comes out to be minus 0.00446, mx is equal to 1.8333, my is equal to 0.765. So, these are the values we have calculated using the relations earlier, and now from this Ex, Ey, all these properties we can calculate epsilon x. So, epsilon x comes to be minus 483, epsilon y comes to 705, and gamma xy comes to minus 443, and all this times 10 to the power of minus 6 microstrains. So, this is how we do the computation, and I hope you will find these lectures very useful in terms of computing the strains if you know the stresses in an xy plane for a generally orthotropic plate. Next week onwards, we will develop this theory further, and we will start working on a formulation which will help us analyze not just single layers, but actually laminates of entire systems. So, that concludes our discussion for today, and I look forward to seeing you tomorrow. Thank you.